Okay, let's just get started. Okay. Um, I'm Jerry Dai, and this is my introduction, and I'm going to be teaching you all today because is Chris coming? I don't know if Chris is coming or not, to be honest. And it looks like that we have how many students? Wow, 5 students, 6 students. I'm shocked. Okay, it looks like we have a very large class today. And yep, this is Chris Penn's introduction. And today our topic is pigeonhole principle, which is a pretty common it's a pretty commonly used theorem in Olympiad math. And I think the main takeaway from pigeonhole principle, if you get one thing from this lesson, just remember this. The main point of pigeonhole principle isn't that it's supposed to be some theorem to be memorized and used. Because there's no theorem in the name, right? It's not a theorem. It's more intuition that you can use to solve problems. And what do I mean by that? Sometimes when you're doing problems, you'll have some properties of the things you're trying to prove, like the objects you have. And then those properties, if you can separate those into categories, and if you have a lot of objects, then you might be able to place them all into different categories and then use pigeonhole. So that's the main point of pigeonhole principle, and I'll just explain what it is quickly. So pigeonhole principle is if you have n plus 1 items and you want to place them into n boxes, which are the categories I was talking about earlier, then at least one of the boxes has 2 items. And the boxes and items, I don't think that's a super good name for what pigeonhole principle is, because the items are really just any type of object. They could be numbers, they could be trees on the grid, they could be, I don't know, pigeons. And the boxes are just categories that we can place those objects into. So the example below, if there are 6 counters in a 5x5 grid, then choosing the counters as the items, which are the objects, and the columns as the boxes, which are the categories, tells us that there's at least one column, which is the category, with at least 2 counters, which is the object. So you can think about pigeonhole principle in terms of objects and categories. And what's most important is that the categories, sometimes there aren't enough categories to put all of the items into different categories. So that's when you get 2 items in the same category. Okay, and that was the basic version of the pigeonhole principle, where you had 2 items in a single box. But what happens if you have more items, right? So if you have kn plus 1 items, which is to say one more than a multiple of n items, and you have n boxes, so n different categories. And what we know is that at least one of the boxes has to have at least k plus 1 items. And the k plus 1, firstly, because there's kn plus 1 items, which is greater than kn, then at least one box has to have k items. And in fact, the equality case, where all of the boxes have the same number of items, is when there's k items in each box. So all boxes must have at least k items. And if there are k items in each box, then we know that there are k items in every box. Okay. And now we can look at the plus 1. So what does the plus 1 actually do? Well, firstly, we have 2 cases. Either there are k plus 1 items, either when we place the first k in items, there were k items in each box after we finish placing them. In that case, if we place the single item into any box, then it'll increase the number of items in that box by 1. And there's going to be k plus 1 items in that box. And if we didn't have that arrangement, then there must have been at least k plus 1 items in a single box after we place the first k in, and the last item doesn't matter anyways. So in either case, at least one of the boxes contains at at least k plus 1 items. And yeah, the example below demonstrates that if we have 13 apples, 3 children, well, 13 is equal to 12 plus 1, and 12 is equal to 3 times 4. So there's 4 times 3 plus 1 items, and the children can be the different boxes or the different categories. So there's 3 categories, and therefore k is equal to 4. So at least one child has k plus 1 equals to 5 apples. And you can see a proof of this below. Assume for the sake of contradiction that they all have fewer than or equal to 4 apples. Then that means that there are fewer than or equal to 12 apples in total, which is going to be a contradiction. Okay, and this is the last part of pigeonhole principle, and I think it's not super important because when you're dealing with infinity, right, then you can just make k as large as you want, and the infinite pigeonhole principle just kind of takes takes the case where you make k very very big as you want, and it just extends it to infinity. Like technically infinity isn't a number, you might have heard that, but if we have infinite items and we have a finite number of boxes, then at least one box has an infinite number of items. And why is this? So let's just prove this quickly. So if every box has a finite number of items, then we know that there are a finite number of boxes. So we also know that the total number of items is finite multiplied by finite, which is just still finite, which is a contradiction to it being infinite. Oh dear, April is typing. She's going to say something. Okay, anyways, um, and you might have also heard of Hilbert's Hotel, the hotel with infinitely many people and infinitely many rooms. And you might also know, if you watch that TED Ed video, that there, if we already have an infinite number of people in the hotel and there are an infinite number of rooms in the hotel, like I said earlier, then if one more person arrives, then we can fit one person to every room just by shifting everybody forwards by one. And this is not a demonstration of pigeonhole principle because firstly, everybody is in separate rooms, but it's also not applicable to pigeonhole principle because there are an infinite number of boxes. So pigeonhole principle only works when there are a finite number of boxes or categories. Unless you want to get into ordinals, I guess, but yeah, I don't know why I said that. I was just padding for runtime. Okay, anyways, now that you know kind of the gist of pigeonhole principle, we can do some problems. So Jimmy has a drawer with n different pairs of socks, and how many socks must he draw before he can guarantee he has drawn a matching pair? And this is a pretty classic problem. You might have seen it on the Otago problem solving challenge, but I'll give you all about 2 minutes to work on this problem. And if you have the answer, just say it in the chat. Like every lesson, nobody talks in the chat, and it makes me so sad. What schools are you guys from, by the way? I just need to get a sense of our demographics here. Okay, Kristen, interesting. Yeah, both of the people who said something were right.
I'm sure we don't need to give them that much time for this. It's okay. If we run out of time at the end, we can just like go do a bonus lesson on coloring or something.
Okay, but I haven't looked at the problems on the handouts.
On those front, yeah, I'm sure you'll be able to like insist solve those.
Real? Okay.
I don't know the answers for those either. I just put random questions. It's okay.
Wow, so true. Okay, whatever. I think that's enough time. Let's go to the Jamboard, and
Oh,
I
sorry.
will
Can you send the
split.
Jamboard link in the chat again?
Oh yeah,
I
you're right.
missed it
I should
earlier.
do that.
Cool.
Okay,
Thank you very much.
share. Okay, I'm going to spend a long time drawing out Jimmy socks in detail. So there's enough time in this lesson, so I don't have to do anything else.
We're talking through the
But
problems. The problems get hard later. Yeah. You can give them more time for
no,
this.
they're all like 5-liners. Okay, anyways, here's Jimmy,
I know, bro. Turbo was like 5 lines.
and here are his socks. Okay, and he has how many socks? 2 in socks. Okay, so Jimmy has numbers on each of his socks, all the way up to n. And let's see. And because socks come in pairs, he has 2 socks for each number. Dot 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 in. Okay, and so can somebody tell me what are the pigeons in this case? What are the items? What are the items that we are placing into boxes or categories in this scenario? Exactly. The socks are the items that we are placing into boxes. And what are the, I'll just call them categories from now on. What are the different categories? Okay, well, what are the different categories that we want to place the socks into? Because we have n plus 1 socks, right? So how many categories do we think that there are going to be? Yeah, exactly. So each pair of socks is its own separate category. So let's imagine when Jimmy takes the socks out from his box, he has a separate box for each pair of socks. Okay, so let's say that Jimmy picks up sock number 7, then he would place the sock number 7 in box number 7. And when he has 2 socks in the same box, then we know that he has drawn a pair of socks. So we have n boxes or categories. Okay, I'll just call them boxes. Categories is too hard to say. There's n boxes, and we want 2 items in the same box. So we need n plus 1 items in total. And therefore, the answer is n plus 1, because drawing n plus 1 socks makes us guaranteed to put 2 socks in a single box. And if we really wanted to be rigorous, we could prove that if we drew n items, it wasn't enough to make a pair of socks, because our answer is n plus 1, but you have to prove that the answer is both sufficient and necessary. So we've proven that drawing n plus 1 socks is sufficient to guarantee that there's a pair of socks in a box. But we have not proven that n socks is sufficient to put, we haven't proven that n socks is impossible to get like 2 socks in the same box. So I'll just go through this quickly and prove why n plus 1 socks must be necessary. So if we have a single sock in each box, then obviously there are n socks, but There's no pair of socks anywhere. So that's why the answer isn't n. Therefore, our answer is n plus 1. Okay. Now let's go to the next problem, because this is just going to be a problem session, because there's literally nothing to teach on Pigeonhole Principle except for doing problems. And let's do problem 2. So if there are x integers and all of them are between 1 and 2n inclusive, what's the smallest value of x such that we can guarantee that there exists 2 elements of S which are co-prime? Okay. I feel like this is sort of similar to the sock problem. That can be your hint, and I'll give you like 2 minutes to work on this problem. And if you have the answer, just type it to me in the chat. I would be very excited to have more people talking to me in chat.
Okay, I mean, I think for like these questions, right, it's always good just to like start off maybe with a fixed integer n, like maybe say something like n equals 4, and just play around with it for a bit to try to get a bit of intuition on what you might think the answer is. So
So
if you choose, I mean, like I'm choosing n equals 4 as like some number that's like small enough to work with, but not too small that such that the problem is trivial, right? Um, so if you choose n equals 4, you have x integers between 1 and 8. And maybe what you want to do is you want to see like how many numbers you can choose such that there aren't two that are coprime, right? Um, like you want to see how big can you make x such that it doesn't satisfy this criteria of two elements being coprime. So
and
like, does
before
anyone
we
have any
continue,
ideas? Sorry.
wait, does everybody know what coprime means, firstly?
Oh yeah. Hope you've been attending the number theory lessons. You know,
Yeah. Who teaches number theory again?
Jane Hawken.
Yeah, they're not
Yeah, I
learning
wouldn't blame
anything.
them for not attending. So.
Okay, so does everybody know what coprime means? Speak now or just be lost, Say in private chat
Oh, okay,
if you
okay.
don't.
Amy says not really. That's fine.
Well, do you want to
Okay.
explain?
Yeah, okay, I'll explain. So what coprime means is two numbers are coprime if they don't if they don't share any common factors. So for example, 2 and 4 are both multiples of 2. They both have a factor of 2. That means that they're not coprime. But maybe 2 and 5, for example, would be coprime because there's no like prime number that divides both of them, right? Like the only number that divides both of them is 1, but we don't really count that. So yeah, so co-primeness is a quality of a pair of numbers, like two numbers like are co-prime relative to each other.
Yeah, that's very true.
So like maybe what we want to do with this is let's try choose a set of like numbers as many numbers as possible, such that they're all like not co-prime to each other. Like, does anyone have any ideas of how we can create like a large set of numbers with like such that no two of them are co-prime?
Wait, Lily has a question. Okay, Lily says, how useful do you think pigeonhole principle is in NZMO2? And I think,
Oh,
I'd
in
say it's
fact, I
very
think
useful.
okay, wait. I just want to have input. A pigeonhole principle came up in NZMO 2 2020, 2021, and 2022. So
Wait, did it actually?
wait, 2022? Yes, I did. It came up like as a prominent feature in three consecutive years. I put all the questions
Wow.
on the handout and the slides.
3 consecutive years. Wow. Okay. Like I feel like, well, obviously it's useful if the problems are there, right? But what I would say is, for pigeonhole principle, as you do more problems, you'll naturally encounter more problems involving pigeonhole principle. So, like, you can't really rank Olympia techniques based on their usefulness, because sometimes you might know the approximate technique that's going to be used to solve the problem, right? But then because you don't make a crucial observation, then you're not able to solve the problem, even though you know the technique which should have been used to solve that problem. And sometimes you'll know the technique and you won't see that the problem needs you to apply that technique. So for example, like lifting the exponent, I think I know the statement of lifting the exponent, but
Mhm.
sometimes when a problem uses lifting the exponent, then I don't know how to solve it, because I don't know that lifting the exponent is supposed to be applied in that situation. So what I would say is, don't focus on ranking Olympia techniques in usefulness. I think what you should do is you should focus on, I don't know, just doing problems,
Yeah.
and
With that said,
learn the techniques. Facts.
I know Jay just said not to rank Olympiad techniques. However, I think pigeonhole principle is very, very useful. Yes, it would rank highly if you were to rank
It
them. Not saying you
is. It is.
can, but maybe if you could hypothetically, I think it would be quite high. Actually, also,
Hypothetically,
yeah, 2021
if
might not have been pigeonhole. I'm not sure. It was like sort of. It had a
no, I think
pigeonholey ideas, right? Even if it wasn't explicitly pigeonhole.
what
I
is
think the main thing about
remainder
pigeonhole is just remembering the idea when you're solving like combinatorics problems.
facts like Chinese remainder theorem.
Yeah, like the notion of just like many items and like when you have too many things fitting into like too small like categories, then like there must be like some kind of overload. Um, okay, so I'll just okay, I guess I'll just go through like maybe a thought process you might have since no one really gave any ideas. Um, so one thing you might notice is that if you just look at two like random numbers in here and see if they're co-prime or not, it's kind of easier to get like um if you want numbers that aren't co-prime, it kind of feels like the odd numbers are like easier to like be co-prime too, right? Like if you choose three, like three is co-prime to like 1, 2, 4, 5, 7, and 8, right? It's co-prime to so many things. So you probably don't want to choose three because if you choose three in your set, when you're trying to make like this when you're trying to have this quality where no two elements in your set are co-prime, choosing three would really restrict your other choices. Because then if you choose three, you can't choose one or two or four or whatever. On the other hand, if you choose two, then you can still choose any even number. And I think if you like consider this idea, right, about the even numbers, you might realize that, hey, you can put 2, 4, 6, and 8 into a set, and you can't find two numbers that are co-prime because all of these numbers are divisible by 2, right? So that construction of a set of consisting of 2, 4, 6, and 8 shows that you can have a set of four integers, so x equals 4, where it doesn't satisfy this property that uh, like no, any two of them are co-prime. So the question, if we go back to the original question, it's asking, what's the smallest value of x such that we can guarantee there exist two elements of s which are co-prime? So x has to be greater than 4, because if x equals 4, we can't guarantee that two elements will be co-prime. So x is at least 5. And if you play around with small cases, you might like conjecture that x equals 5 is indeed the answer, because it's really hard. In fact, it is impossible to have a set of 5 integers when no two are co-prime. So now we need to start thinking why. And a lot of times, right, when you have this idea of like just too many items, like right now, right, we're saying x equals 5. we're choosing 5 elements in our set. It feels like too much, right? It feels like there must be some kind of like crowding, like of just like all these like integers. Like there must be some kind of like co-primeness somewhere in there, right? Whenever you have this kind of idea of just having too much overload into like a system, like that's when you might want to start using pigeonhole, right? You're putting too much stuff into too small of a space. So when you have this idea of like pigeonhole in your mind, you can start looking for pigeons and pigeonholes, or items and boxes, or you know, like objects and containers or whatever, right? Okay. So, what do you think our pigeons are here? I think this one is, somewhat of like the obvious answer here is just correct, right?
So true.
What are the items that we're placing into boxes?
What you're thinking is probably correct, so just say it.
Okay. Well, what I'm thinking.
No, wait, Chris. Let them think. Let them think.
Okay, sorry. Oh yeah, I got an answer from Isabel.
Oh
Right?
my
Yes,
gosh,
yes. The pigeons are the numbers.
So
true.
true.
That's good. So the items, the things that we're placing inside our boxes are the numbers, right? That's what we have a lot of. We have at least 5 of them, right? The pigeonholes here that are a little bit less obvious, right? We want, okay, so when we're designing these pigeonholes, what we want is this property. If we put 2 pigeons inside of 1 pigeonhole, they're guaranteed to be co-prime. So, like, under what conditions are 2 numbers like guaranteed to be co-prime? Like what's like the simplest condition you can think of for 2 numbers to guarantee be co-prime? Yeah, sure, Shannon prime factors. I mean, that is the definition, yes. But it's hard to make pigeonholes out of this like quantity, right? Yes, 2 prime numbers as well. That's another good one. Um, if there were a lot of prime numbers, yes, we could make pigeonholes of just 2 like of prime numbers. But there's only, I think, what, 4 prime numbers in here. So like the composite numbers, you wouldn't really like, you need to find a way to deal with the composite numbers as well, right? That's a nice drawing of a bird there. Um, I guess I'll just say like what you might notice when you're so like you might want like gain this intuition when you're trying to design a set that don't contain numbers which are co-prime. And that this is the reason, like what a reason why it's really good to play around with the problem and try to gain a bit of intuition yourself, right? So when I'm like let's say I'm designing a set from 1 to 8, I'm choosing some numbers. I don't want any 2 to be co-prime. I choose the number 5. I mean, like what you might notice is that if I choose the number 5, now I can't choose the number 4, nor can I choose the number 6, right? Like, is it easy to see why 5 must be co-prime to be to both 4 and 6? Yes. Okay. Well, yeah, because there's no prime factor that divides an integer n and an integer n plus 1. If it did, it would have to divide the difference as well, which means it divides 1, which is the contradiction. So any 2 consecutive integers are always co-prime. And that's a very important, like, well, very key observation here. What it means is that you can split this like string of 8 integers into little like chunks of 2 integers, right? These are your pigeonholes. So one, partition, like one pigeonhole might be just the set 1 and 2. Wait, Jared, can you just like draw? So if we split the numbers from 1 to 8 into 4 groups of like 2 consecutive numbers each, 1, 2, 3, 4, 5, 6, and 7, 8. If we ever have two numbers that are in the same pigeonhole, for example, if we have both 3 and 4, then we're of course guaranteed to have two numbers that are coprime because we have two consecutive integers, which means we have two integers that are coprime. But remember, we had n plus 1, or in this case, 5 integers to split among our 4 pigeonholes. What does the pigeonhole principle tell us? Yeah, you have 5 items, 5 pigeons, split into 4 pigeonholes. Well, that's too many pigeons for these 4 pigeonholes, right? One of them must have at least 2. And once one of them has 2, then you're done, right? So if you have 5 items or 5 pigeons, you must have 2 numbers that are coprime. So that shows that x equals 5 is the answer, right? Because we showed that 4 isn't good enough. 4 is not big enough, but 5 is big enough. In general, for I hope you guys can see why this argument would generalize, right? So for the general case where you have 2 n integers, n integers isn't enough because you can just choose the n even integers, but n plus 1 integers is enough because you can set up your n pigeonholes 1, 2, 3, 4, 5, 6, so on, right? And you split your n plus 1 pigeons amongst these n pigeonholes, and you find that 2 of them must be coprime. So the answer is just n plus 1 for the general case.
Okay. Yep, that was a pretty good problem. Very exciting stuff. Okay,
yeah, I think the key thing to take away is that like you want to try to develop some kind of intuition for when you want to try using pigeonhole, right? Like you need to know when to use certain techniques. I said it before, but like a good indicator for like, well, for me at least, a good indicator for trying to use pigeonhole is just that this notion of like too many things, right? That like it feels like something must like clutter up and like congest somewhere. And then you can try looking for pigeonholes. And you want to set up your pigeonholes with a certain property. Like, for example, we set up our pigeonholes in the last one with the property that any 2 pigeons in a pigeonhole must be coprime. So that's kind of what led us to like putting up pigeonholes as 2 consecutive integers. Okay, I'll wait this problem.
Okay,
Okay,
so let's do 3.
This problem's not that deep. I think this problem's a bit easier.
And I have very good memories of this problem.
Oh, okay. So someone asked, how do you know how to set up the pigeonholes? Well, I mean, that's kind of the hard part, right? That's what makes an Olympiad problem require problem solving and creativity. You do it by like so you know certain properties that you want your pigeonhole like to satisfy, right? Like I said last time, the property I wanted my pigeonholes to satisfy is any 2 numbers in the pigeonhole must be coprime. But the other thing the pigeonholes must do is they must cover the entire like space cleanly, right? The reason that prime numbers didn't work is because yeah, I can make a pigeonhole consisting of like 3 and 7, which are 2 prime numbers. But then like a number like 8 wouldn't really like I wouldn't be able to form a pigeonhole out of it. The reason the 1, 2, 3, 4, 5, 6, 7, 8 partition was so nice is because it like cleanly tiled the entire like space of integers. So you want to just I don't know, like I guess you kind of want to ask yourself, like what is like a clean or like like a simple way of like describing or knowing when 2 integers are coprime. I think in this case, like 2 consecutive integers being coprime is a very like clean, very simple way of just setting up like these boxes. But yeah, it's not easy, right? So you gotta do a lot of problems, right? You gotta think a lot. You gotta yeah, solve problems. Um, yeah. By the way, I think for this problem, just a bit of a hint, just so you guys don't like waste too much time. I think it might be higher than you think, like the maximum number of counters. Um, yeah, just a word of advice, right? Don't like keep your mind open, right? Like don't always think you've found the best bound when maybe you haven't. Um,
Yeah, that's how Chris tricked me with this problem.
yeah, okay, cool. I think people got the answer now. Yeah, Jay, you just want to like present the answer. I think this question's not that deep.
So true, so true. Okay, let's do the question. And I will draw a tic-tac-toe grid.
Yeah, I mean that's like
Correct.
kind of a motivation situation. It's like tic-tac-toe.
Wait, didn't
like-
it say it was tic-tac-toe in the problem?
It did not say it was tic-tac-toe in the problem, I don't think.
Oh,
But like
did
that's
it
kind of
not?
the source.
Okay, so first, let's try and do the upper bound, right? Let's ignore the diagonals for now because they're kind of complicated. And
Wait. Well, I think the construction's like easier like to do first.
really? Okay, fine,
I'm
fine,
not
fine.
easy to do. I feel like it's more motivated. It's like you're just playing around and you find the construction first and then you try.
Okay, when I first did this problem, I thought the construction was going to be this. So I thought the answer was 4, and that was like 1 month ago, which was sort of embarrassing. But then I realized that this was not the right answer because Chris told me. And so that's the main question. How do we come up with the construction for this problem? And if you just add random stuff into the grid, it's a bit, I guess it's not super hard, but then like you see now we run out of spaces. It's not hard at the start, but then once you kind of like you're always sort of left wondering, right? Can I do any better? Because in this position we have 5, but if we place an extra thing anywhere, then it's not going to work. So let's restart. And what we're going to do is we're going to start with a full grid of crosses, and we're going to try and take away some of the parts. And what can we take away? Well, one thing we might do is we might remove the center square, since that's the one that's in the most, 3x3s, right? And now we only have to care about these ones. And note that the ones on the corner are both in, this one covers these two, and this one covers these two. So if we remove both of these, we're done. And that's our construction. So now let's prove the construction. So assume, for the sake of contradiction, that there are 7 crosses. But then there are only 3 rows. And 7 is equal to 2 times 3 plus 1. So one row has 2 plus 1 crosses.
Yeah, like if you have 7 crosses and you're trying to fit them into 3 rows, you can't possibly have all 3 of them having fewer than or equal to 2 crosses, right? Because that only makes up 6 crosses in total. That only accounts for 6. Because there's 7, there must be a row with 3 crosses, which is 3 in a row, which is bad. Okay.
Yeah, that's so true.
Great. Okay, we
Okay,
can go to the next question now.
let's do the next problem.
Yeah, stupid question. Okay.
No, this question is too hard.
This one's too hard. We
Wait,
skip
cite
it.
no, cite the Ramsey theory.
Real. Tell me go. Wait, you guys can read PST and see how those questions. Okay.
Okay, let's give them some time to work on it. Let's have faith in our students.
Yeah. No, it's not, I don't not have faith. I just said like there's some PST. I feel like half these guys probably already read PST.
That's true.
Um. Okay, I think this question it's a bit weird to think about, right? I'll just give like a bit of a tip on how you can frame it. I think an easy way of like framing it is imagine the six people as like six vertices, right? Or like, would you guys know what like vertices and edges are in terms of like a graph? Yeah, okay. So it's just like imagine the six people was like 6 points like around a circle, like six vertices, and then maybe like connect two vertices or connect two people with a line if they're friends. And we're assuming that friendship is mutual. So like if I'm friends with you, you're friends with me. Yeah. Another way you can think of it is like, yeah, okay. I think this problem's pretty well known. I don't know. We can kind of like go through it quickly if you guys have already seen it. We do have
I don't
like,
think they've seen it.
okay, really, you're that confident? Okay, we do have
Yeah,
like quite a few other problems there to go. Yeah.
it's fine. You can never do you can never talk too much. Oh, somebody's seen the problem. That's
That's what I'm saying. Man. Oh, good, good.
okay.
She's lying. It's okay.
Okay, let's go through it quickly. Let's go through it quickly. And right. So there's a party of six people. One, two, three, four, five, six. And either three of them are friends or three of them are not friends. So let's say that if they're friends, then they're connected by a red line to symbolize the red string of fate. And if they're not friends, then they're connected by a blue line to symbolize how they don't know each other. And I'm not gonna go into that, but and now we want to color each line in the diagram such that it's either red or blue. So wait, how do you do this one again? Like it's like if you have free if you have free things, right? Note that by pigeonhole principle, since each vertex has five connections to another vertex, then there are either three red lines or three blue lines. And without loss of generality, let there be three red lines to yeah, so there's
Yeah,
three
yeah, yeah.
red
Okay,
lines,
wait, sorry.
right?
If I could just point out something. I think in some of the problems we just did previously, like the pigeonhole principle might be like, a key part of the solution or like the main step, right? I think in a lot of problems, like pigeonhole principle might just be like a small step. Like it's not like super like the main part of the problem, right? The main part might be something like some other observation or some like other step that's like harder. And pigeonhole principle might just be like a small like helping step in the middle. So I think it's good to like always like you really want to like make sure that you can like you're really comfortable with it and you can kind of just like see it really quickly and be able to like make intuitive sense, right? Like not have to like think about like the pigeons and like pigeons and like pigeonholes every time. Sometimes it's like okay, if there's two colors and then there's like 5 edges, right? At least 3 of them is going to be one color, right? Like, or at least like 5 of the edges is going to be one color. Like, you want to like be comfortable with an enough to the point where that seems intuitive, that seems obvious, and you'd be able to like reach that conclusion like very easily, right? But yeah, anyway, I think what Jerry was saying is very true.
So
If you
true. And what we have is that, um, okay, so 3 people are connected to this person by red, right? So now let's look at the connections between these 3 people. So if all of them are blue, then obviously we're done, right? Because we have a blue triangle, which means that all 3 of
no,
them are not friends
wait.
with each other.
Mhm.
But if any one of them is red, then we also have a red triangle because they're both connected to red and they're also connected to each other. So we're also done. So that's the whole problem. Yep.
Wait, sorry, did you just understand that? I think Jay went through that pretty quickly.
Ah,
Yeah, the basic
so
idea is that if you translate the question in terms of vertices and edges, so red being a friend edge and blue being a not friend edge, then the question statement prove they are a group of 3 people who are all friends, or group of people, none of whom are friends, is equivalent in this new like translation of the problem to prove there's either a red triangle or a blue triangle, right? So what we've shown here is that there must exist either, a red triangle somewhere or a blue triangle somewhere. And okay, so someone asked, what would the formal proof of that look like? So if I was writing a proof of this, I would say, okay, consider, an arbitrary person A, right? That's the person here in the top left. They have 5 friends, right? So I guess if we've already like kind of established this red and blue like edge thing, so okay, maybe at the start of the proof, I'd write something like, let the 6 friends, be denoted as like 6 vertices. Draw like a blue edge between 2 vertices if they're not friends, and draw a red edge between 2 friends if they are. Sorry, draw a red edge between 2 vertices if they are friends, and then make it clear that the original problem now is converted into this new problem where we're trying to prove there's either a blue triangle or a red triangle. Okay, so then you'd say something like, okay, consider an arbitrary person A. It doesn't really matter. There's Well, an arbitrary vertex A, right? Because people have been turned to vertices now. There's 5 edges coming out of this vertex, and there's 2 colors, red or blue, right? So by the pigeonhole principle, there must be at least 3 edges that are the same color. Then, because the problem is kind of symmetric in blue and red, I'll just say, without loss of generality, let this color be red. So there are at least 3 edges coming out of this one vertex that are red. Okay, now consider like the 3 people that these 3 red vertices connect to, right? I guess you can give them names, right? Like like people B, C, D, whatever. Um, if any 2 of people B, C, D share red edge, then uh, like those 2 people, along with person A, form a red triangle. If no 2 of the people in B, C, D share a red edge, they must all share a blue edge, and therefore BCD forms a blue triangle. In either case, you have either a red triangle or blue triangle, QD, you're done, whatever. Okay. Yeah, so just go through, like when you're writing proof, just go through all the logical steps, right? Make sure that every case is covered. So you explain like 100% why it must always be true, right? Why it must always be the case there's either red triangle or blue triangle. Okay, great.
oh wait, Lily asked me a question. I didn't reply. How do you know you should use proof by contradiction? That was from problem 3, right? Okay, so we know that we should use proof by contradiction in this case because we know that the answer is 6, right? By our construction. So what we're doing is we're proving that we can't have 7 crosses by assuming that we have 7 crosses. And then after we assume that we have 7 crosses, we show that it results in a contradiction. So When you want to prove that something is not true, most of the time, that's when you use proof by contradiction. Okay, let's do the next problem now. Yeah, problem 5. Yeah, I think I know how to do this one. Show that among
I
any
hope you know how
inputs
to
to
do it,
integers.
because I'm going to the bathroom, so I'm going to be back in like 5 minutes.
No, it's all good. Okay, fine. You can do it then. No,
Yeah.
let them try for 2 minutes. Okay, is that enough time for them? Okay, should we just get on with the solution? Because I think that should be enough time for them. Okay, well, Chris is not responding, so I guess I'll just go for the solution. So show that for any n plus 2 integers, there exists 2 whose sum is divisible by 2n, or 2 whose difference is divisible by 2n. So, okay, so in this case, what we want to do is, firstly, the presence of divisibility by 2n shows that maybe we should take it mod 2n. So let's do that. Let's look at the numbers mod 2n because that's when it's easier to like do divisibility stuff. So, okay. So now we have 2 cases, actually 4 cases. So a number is either 0 or it's 1 to n minus 1, or it's n plus 1 to 2n minus 1. Okay, so let's put them into pigeonholes. And what we're going to do is we're going to do pigeonholes such that if a number, okay, firstly, if a number, if a modular, what was it called again? If a number mod 2n gets repeated twice, like let's say we have 2 numbers which are both free mod 2n, right? Then their difference is going to be divisible by 2n. So you can't have 2 numbers which are the same. And what we're going to do is now we're going to split them into pigeonholes. So let's say that our pigeonholes are 0, 0, and n, and also 1, 2n minus 1, and also 2, 2n minus 2, dot, 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 n minus 1, n plus 1. So what we're going to do is now there are this is 2 pigeonholes, and this is a total of n minus 1 pigeonholes. And note that we have n plus 2 numbers total. So 2 numbers must be in the same pigeonhole. Okay, but look, if 2 numbers are in the same pigeonhole, then 1 plus 2 n minus 1 is equal to 2n. So it's 0 mod 2n. So for any two numbers that are in the same pigeonhole, then we know that their sum is going to be divisible by 2n. And we know that's guaranteed because there are n plus 2 different numbers. And if the numbers are the same, then the difference is divisible by 2n. So we're done. Okay, any questions? If not, let's go to problem 6. Wait, Chris, how are you supposed to do this one? Are you supposed to use the ratios?
What?
Okay, whatever.
Idiot.
Just try the problem. Try the problem.
Okay, I can explain that. So good.
Wait, are you supposed to use the ratios?
No, you don't.
It's over. Oh wait, okay, I see how you do it. Okay. So true.
I'm going back to scrolling YouTube Shorts.
Can you share screen?
Only one person can share screen. Try me sharing YouTube Shorts instead of the slides.
Okay, how about you call me on Discord and share screen? Wait, what happened to Reels? Why are you scrolling YouTube Shorts now?
Oh, because I'm on laptop.
Oh, so true, so true. Okay, not just. Wait, okay. Let's call in the MindNZ server general channel. Group YouTube
They
Shorts.
they can be no way. There's no way calling in two different calls at the same time is a good idea.
No, I'll do it I'll call on my big computer.
Wait, let's go. I can call my phone and we can go through Reels.
Okay, let's go.
You stupid? No.
Anyways, has anybody made any progress on the problem?
Wait, did you
Without
ask them
using
if
the
they know what
rituals.
mod 2 means?
What?
Did you ask them if they know what mod 2n means?
Surely they know, right? Like, come on. Surely. If they don't know, I don't even want to explain it if they don't know.
No.
Like, okay, surely they do know though. Like, if they don't know, that's tough. They should have showed up to number theory sessions. Wait, Chris.
Yeah.
Wait, why is Xing talking about AMC on Discord?
Wait, Australian one?
No, the American one.
Why not?
Like, I don't know. He's not. I thought he retired. I thought he's retired. Okay. Anyways, I'm gonna go for the problem. So consider all the different residues mod p, right? So note that p is a finite number. Therefore, there are a finite number of residues mod p. Wait, was I sharing screen during the solution? You know what? It's fine. Anyways, assume that there are a finite. So let's take all the numbers mod p, right? And we know that there are infinitely many primes because of Euclid's proof. So let's just consider our boxes to be the different residues mod p.
Like a residue mod p is just a remainder mod p, by the way. Like
yeah.
2 mod p means that it leaves a remainder of 2 upon division by p.
And by infinite pigeonhole principle, there are infinitely many things in at least one box. So we're done. Because if we take like those infinite things pairwise, their difference is going to be divisible by p. Yeah, does everybody understand that?
Okay, at least one person understands. That's good enough, honestly.
Okay, that's pretty good. Like, yeah.
Like one person, like I'm happy with that, honestly.
Bro, what is Xing Yuzhu talking about? Like, look,
Like, what is it?
okay, he's saying, so Mather says that if everybody gets a medal, it's like UK primary school sports day. And Xing Yuzhu says, I mean, that sounds boring too. I guess the brutality is what made it beautiful. Someone like me are destined to be are destined to be sacrificed, and I assume he means
Bro, can you just show the like, can we go do the next problem first?
Okay, let's show them the next problem
Oh
so
wait,
they
let's make
can.
another PST example. Also, it's kind of classic. Okay, there you go.
No, I thought they were gonna reflect on our solution. Okay, let's do problem 7, guys. Are they gonna put this on YouTube?
Yeah.
How many views does mine NZ get on YouTube?
Oh wait, shit. Also, by the way, I didn't like go teach my like Olympiad class at school on Friday because like there were like two people that showed up, and I want to go to market day to go buy some samosas instead. So I told them that I'd just like post like the Mine and Z links on like those like a class page, and then like they can go like watch like the tutorials and stuff. I forgot to give them the link though, so they're not here at this lesson. That's a bit sad.
Wait, Chris, they're getting like more than 10 views.
Yeah, yeah. I'm gonna send it there, and they can go binge watch all the past like lessons. It'll be so good.
Wait, but they're gonna see us doing this.
Nah, okay, okay, and
You're right, you're right. Okay, so Xing Yuzhu says, someone like me are destined to be satisfied. Whatever.
oh, sacrifice. Also, by the way, that math card edition guy is Joe. It's not math.
I know it's not Mather because it's Conan edition. Like, what are you
Oh
saying?
yeah. Anyway, he's Joe. But
Wait, who's Joe?
yeah.
No. Like, no. Which Joe are you talking about?
Joe.
Wait,
Who's Joe?
no. Is it like Joe from IMO? Is there a Joe from IMO?
No. He's the moderator on mods.
Oh, okay, whatever. So,
Like,
wait,
yeah, he
Chris,
made UK camp. He didn't make IMO.
would you sacrifice a team member for the rest of your team to get guaranteed gold, as in killing them? Like, surely not, right? Surely not.
Yeah, well, obviously, what are you surely not? Obviously not. Who's sacrificing?
I reckon like.
Bye bye, Jay.
Okay, what about wait, wait. Okay,
This is so unprofessional. Okay, wait. Does anyone have any ideas on like how to start this problem?
does anybody have any ideas on who we can sacrifice? Also,
Wait, if we had to sacrifice one person in this meeting right now to get guaranteed gold for the rest of us, who's it gonna be?
the proctor. Okay, whatever. Let's do it. They're gonna fire me for being a revolutionary, but let's do the problem. So, has anybody made any progress on the problem? Okay, nobody's made any progress. Let's just do the problem. Okay, so let's consider the sequence 111, 111, etc., etc. And let's consider their residues mod p for any
Oh wait, do
prime.
you want to explain this first or collab like the 2 and 5-ish thing first?
You know what? You can explain it. I want to explain the 2 and 5-ish stuff.
Oh, okay. So what the first thing you can notice, right, is that you can add a bunch of zeros to the end of any number that you want, right? Like 101, you can turn to 1,010 or 10,100, right? Like 101, then you can add any number of zeros. What the effect of adding more zeros to the end of a number is you are increasing its prime factors by more twos and more fives every time, right? So if I have a number like 5 to the power of 100, and I want that to divide some number with only ones and zeros, I can just make a number with one followed by a trillion zeros. And then there's going to be a bunch of fives that divide that and a bunch of twos that divide that, right? So for any factors of 5 and 2 of a number, I can like kind of like deal with those just by adding a bunch of zeros to the end of like my final 1 and 0 number, right? Like if I have a number that's like 2 to the power of 100 times 7, and I know that 1001 says a multiple of 7, then all I need to do to deal with the 2 to the power of 100 factor is just add 100 zeros to the end of my 1001. So because we can just add any number of zeros to the end of a number, we can kind of just assume that we can easily deal with any factors of 2 and any factors of 5. So from now on, let's just assume that our original number, doesn't have any factors of 2 or 5 in it. It's co-prime to 2 and 5. Okay.
Yep. Now let's do the solution. Okay. Let's consider the sequence 111, 111, 111,
We're
mod
mod
n.
in, Charlie.
Okay, fine, mod n. And what we can do is now note that by infinite pigeonhole principle, two of them are the same mod n. Therefore, if we subtract them, minus 11111 dot 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 is going to be equal to 111 dot 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 11 0 0 0 dot 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 dot. Okay, you know what? I'll explain that. I'll explain that. So this is the first term that's equal to like m. It's equal to like k mod n, and this is also equal to k mod n. So therefore, if we subtract them, we get that it's equal to 0 mod n. And you know these are all ones, and these are all zeros. So we're done. And that was by pigeonhole principle. You know, keeping with the theme of this lecture.
Damn, bro.
Yeah. Okay. Let's do
Yeah,
problem
yeah. So
8 now.
I think something to note here, something of interest is for like the past few problems, a lot of the times when you're dealing with like kind of number theory or integer like divisibility kind of problems, it's good to make numbers your pigeons and to make like residues modulos n, or like um your pigeonholes, right? Yeah, so that's
Yeah,
something to
yeah.
always think about. Cool. What's the next problem?
Yeah. The next problem is problem 8. And yeah, wait. This one is basically the same as problem 2. To be honest, like
No,
there's
it's
not
not.
much difference. It basically is.
It's not. No, there's no. Okay, yeah, it's similar, but the pigeons are different, aren't they?
No.
Hmm? No, the pigeonholes are different. Sorry.
Yeah, the pigeonholes are different, but you know the concept is kind of the same. You know, so try the problem for a bit. Wait, Chris,
Hmm?
where did you find that Alex Gunning was trans?
Oh, Ross told me, I think. Well, not
Oh,
trans, but
Ross
Ross
told you.
told me that. Well, I said he for Alex because that's what I thought, but I think Ross said it's a she now. So,
Oh, okay, okay. Wait, Ross is the goat. He's
yeah,
so
Ross knows
inclusive.
more than me. Oh, I could have phrased this problem like, what's the maximum number that we can take, such as like, okay, anyway, yeah, m plus one takes smallest. I
No,
mean,
that's
what's the
kind of
point?
stupid.
It's not stupid because at the end you have to find construction then. Right? I mean, it's pretty easy, but
Nah. Wait, what is Chris saying? I mean, what is Hughes Ju saying, bro?
you know, how am
Wait,
I being conflated with King Ju?
what do you mean deflated with Shinju?
No, how are you conflating me with King Ju? That's
How am I?
disrespectful.
How am I? I'm not. I'm not. It was a Freudian slip.
Yeah, for exactly. Freudian slip.
Anyways, Xing says P25 are the most important problems on an IMO paper, in my opinion.
On God. I
He's
agree.
so right. Wait, how's he
No,
right?
wait, only if you ask. Like, if you're good, then P3 and 6 are the important ones, aren't they now? And
No,
in fact, if you're
because
really
his
bad, then
logic
P1
is
and 4 are the most important. Like, you can't say P2 and 5 are the most important just because
wait,
that's
wait,
something.
wait. His logic is that they decide at least two cutoffs. Is that not deep? Is that not true?
Bro's mad that he can solve either of them.
No, that's sad. That's sad.
Yeah, it is sad, but it's life.
Oh yeah, Chris. Did you
Hmm?
did you also see that D7 is 15 to 20 moles? That's kind of crazy.
How's that crazy?
That just is crazy.
I'm leaving the math and pet celebration Discord server, right?
Yeah, let's leave it.
Wait, no. Wait, no, but here you get a bunch of connections. Damn.
Wait, it's Linus Tang from the United States team. What a goat.
Wait, let's go, friend. Wait,
Oh
bros.
my. Nah, no. I'm not touching the US team ever again. Like, why do you put it in your report?
Because you put in your, I wasn't gonna put it, but you mentioned it, and like you just like it was so vague. You didn't give any details, so I had to fill it
Yeah,
out.
obviously I didn't give you details because I don't remember what happened.
Well, it wouldn't have been. It wasn't really funny because like you didn't like actually say what happened. You kind of just left the viewers like confused. You know.
No, because the confusion is what's supposed to add to the sense of mystery, right? Like, do you know the
Obviously,
noodle
there's no
incident?
resolution. You kind of admit, like, imagine it was a mystery plot, but you just didn't reveal the mystery at the end. At the end, it's just dissatisfaction, isn't it?
No, because it leaves them wondering, like, what happened? Okay, I feel like okay, fine. Maybe I could have given a few more details because oh yeah, guys, you should read all of our IMO reports on the NZMO website. It was a very exciting IMO. Yeah, in fact, all of the IMO reports are very exciting, except for Haltyans.
Yeah, I don't, how they should have written more, bro. He should have like fleshed out his experience with Vera.
Yeah, I thought Haltyn was supposed to be funny. He was not funny.
Holy. I think it was just sad that he like underperformed. Okay, anyway, sorry, we're getting a bit off track here. Okay, cool. Okay, so guys, what do you think the answer is here, guys?
Um,
This one's actually quite hard. I think this one's quite tricky, in my opinion.
yeah, in my opinion, it's tricky. Yeah.
The reason it's tricky is because, right? Okay. Um, so okay, if we go back to problem two, right? If we remember that when we were just testing out like we were testing out certain like sets, right? We were trying to find a set such that we didn't have any two-dollar coprime. And what we did is, what you might realize is that if you had two numbers that were right next to each other, then they would be two coprime integers, and that wouldn't be very good for us. So if we try to play the same game again here with like say like 1 to like 10 or something, right? And you want to create or find a set as large as possible without one being a multiple of another. Well, like what? Okay, I guess it's hard for me to explain like how you would come up with anything, right? But maybe what you would come up with is like you just try to choose a bunch of large numbers because if you choose a number like one, that's not so good, right? Choosing small numbers is bad because small numbers have a lot of multiples. If I choose a number two, I'm very constricted now because I can't choose any even number greater than two.
Yeah.
Oh, wait, I'll send the wait. Do you want to send the page with the results or with the not results with the reports for anyone who wants to watch? See it?
Sure, just send in the chat, and then you can explain this problem.
Yeah, okay. So,
Yeah.
I think the intuition here is that if you choose smaller numbers, that's quote unquote bad for us. If we try to build a very large set, right? So here I'm not really like trying to solve the problem. I'm kind of just trying to get a sense of like how can we build large sets of integers such that no two of them like is a multiple of another, right? So like if we don't want to choose small numbers, let's just choose like the big numbers as big as we can. So if the numbers are say from 1 to 10, maybe I'll choose 10, then I'll choose 9, then I'll choose 8, then I'll choose 7, then I'll choose 6. Okay, so I've chosen four numbers and clearly none of those divide each other, right? 6, 7, 8, 9, 10. Because the largest number is less than twice the smallest number. So clearly like none of them is going to be a multiple of each other, right? And you can't really continue with the strategy anymore, right? Because if I try to choose 5, then I'll have both 5 and 10, where 10 is a multiple of 5. So that's bad. which is good, right? The problem statement is correct because if the problem statement is to be trusted, you can't choose more than half the numbers without running into a problem. And maybe you try some other things, right? Um, like 10, like whatever. Like maybe you skip out on like 10, you go 9, 8, 7, 6, 5, and you choose 4. But then now 4 is exactly half of 8. And if you keep trying this process, you might realize that normally what seems to be happening is you get one integer that ends up being half of another. So in the first case, we ran into an issue when we had both 5 and 10. Then in the second time we had an issue, we had 4 and 8, right? So like maybe you have this like idea of like using when numbers are exactly like double another number. This question is actually hard because the pigeonholes that we have to use aren't obvious at all. So the pigeons, the items that we're sorting into these pigeonholes, is again um just these numbers, right? The integers. That's been a pretty common theme throughout all these problems. The numbers are the pigeons. But here we have to figure out what the pigeonholes are. And the pigeonholes here aren't obvious. They're not nice. They're not super clean. Um, but what we have to do here is we kind of have to like exploit this idea of like of doubling, right? So like yeah, I don't know how to motivate it. Oh well. Should I just give the answer?
Yeah, just say the answer.
Okay, so the answer is it goes like this, right? Imagine one pigeonhole. These pigeonholes, the reason I'm saying they're not nice is because it's different from the other one in that these pigeonholes aren't the same size. We have some large pigeonholes and some small pigeonholes. But as long as two numbers are in a pigeonhole, you're good to go. So one of the pigeonholes is you start with an odd number, 1, and then you just keep doubling it until it goes outside the bound. So 1, 2, 4, 8. Um, oh wait, let's use an actual example. Like let's say we're doing the numbers from 1 to 20. Like one to like
Yeah, 1 to 20. Okay.
yeah, sure. So we keep doubling every odd number until we until it's like it's gonna like escape the bounds of like n equals 20, right?
Yep, we do that.
Oh wait, it should be 2 n equals 20 by the way, because I think it's yeah. So yeah. And what we see here is that we have exactly 10 pigeonholes, and the reason we have exactly 10 pigeonholes is because there are 10 odd numbers, right? Also know that every number is contained in a pigeonhole because every number can be expressed as some odd number times a multiple of 2, right? Like just keep taking out factors of 2 until you reach an odd number. So we partitioned all of these 20 integers into these 10 pigeonholes. And the reason these pigeonholes work is because if you have two numbers that are in one of these pigeonholes, they're clearly one of them is a multiple of the other because the way we're generating numbers in these pigeonholes is they start with an odd number and you just keep multiplying by 2. So any two of these is going to be like the larger one is going to be some multiple of 2 bigger than the smaller one, right? For example, if you choose, like 2 and 8, 8 is exactly 4 times larger than 2. Or if you choose like 5 and 20, 20 is 4 times larger than 5. Or like 6 and 12, right? So I think it's pretty easy to see that if you have two numbers from the same group, from the same family, from the same pigeonhole, right? Like maybe from the one family, right? 1, 2, 4, 8, 16. Then one's going to be a multiple of the other. And we've kind of designed the pigeonholes to be that way, right? Because we've designed them to be like starting from a base odd number and multiplying by 2 every time. So by the pigeonhole principle, since we have n plus 1 numbers, one of these pigeonholes must have at least 2 numbers. And then we're done. Because if a pigeonhole has 2 numbers, then one must be a multiple of the other, right? So I think this one is it's quite tricky to motivate. Um hmm.
Yeah, now it works basically.
I mean it just works, right? But like why does it work? Why should you have thought of this? Jerry,
Honestly, like I think it's sort of the same stuff as before, right? Because you know that Odd numbers are the hardest. So I think like the reasoning is kind of you should base the pigeonholes around them, since odd numbers are the hardest to get to divide each other.
Yes, I think something else that's good here to know with pigeonholes is that you kind of want your pigeonholes to be large, right? If I have a bunch of small pigeonholes, like I want as few pigeonholes as possible, right? Because if I have as few pigeonholes as possible, like I want the number of pigeonholes to be smaller than my number of pigeons, right? Like otherwise I can't really do anything with the pigeonhole principle. So I want my pigeonholes to be kind of large. Like I could have done like 1, 2, and then 3, 6, and then 5, 10 as like each of these is individual pigeonholes. But then at the end of all that, you end up with too many pigeonholes. So it's kind of nice when you have this long chain 1, 2, 4, 8, 16, where you have five integers all in one pigeonhole, such that if you choose any two of these five, then like one divides the other, right? Um, in fact, because we have such like a big pigeonhole at the start, that allows us more room to have these small pigeonholes at like later on, 11, 13, 15, 17, 19, which only have one like item in each, or like one like number in each of them, right? Um, and like the reason we were able to like make these like long chains or these longer chains at the start is because like two is kind of the smallest number, right? It's like the easiest, it's like the smallest like way of like creating more multiples like in like a longer chain without like going too big, right? Like if you multiply by three every time, 1, 3, 9, then you can only get three numbers before the chain breaks. But if you're multiplying by two every time, 1, 2, 4, 8, 16, you get five numbers before the chain has to break, and that's good. Like you want bigger pigeonhole, like you want bigger pigeonhole because um that allows for fewer pigeonholes, which is good.
Yeah, 2 is the smallest number you can multiply by. So that's how you do the problem.
Okay. Wait, did Jerry ever send the whatever
Mhm.
the reports?
I thought you were gonna send them.
Well, I thought you said you told me to yap about like with Austin.
Yeah, you sent them. Okay, guys, let's do problem 9, and this is actually an NZ02 pass problem. So I think it's time to lock in and really take a good crack at it.
Oh wait, should we do this or should we like let them like muse over it
Yeah,
themselves?
we should let them try it. We should let them
No,
try
no, I know, but
for
like should we like just go
6
straight to
minutes.
question 10? Because like question 9,
No,
like shouldn't we let them like do ends in mode 2 like if they want to mock it themselves like without ruining it? Like question 10 is
okay,
like
that's true. That's true. Okay, let's do question 10, and we'll give you guys 5 minutes to try this problem.
Wait, it's so sad. Lily wanted the. I told Lily I'll send the ends in mode like reports, but then like she left the meeting before like I had time to send it, so she's never gonna read it.
That's so
Wait, no one's ever
sad.
reading those. There was like one person that wanted to read it and she left before like. Bro, it's because you didn't send it fast enough. Bro, I can't believe it.
Wait, like I can't even tell the guys on mods to read it because I mentioned seeing you in the report. Like,
You idiot! Why'd you do that? Like, like it's not the fact that you mentioned him. It's the fact that you said he was famous for being sad.
no, I said he was famous for being. Wait, didn't I say he was famous for yapping?
Where did you say it, by the way?
I don't know. Just do control search.
Wait, did Josie take it out?
Surely not. No, no. Also in the XDX hub, I made
Oh, no,
pause six.
never mind, never mind. Wait, no, I swear she took it out.
Oh wait, no, she didn't. What did you say? Just control F famous.
Okay, no, oh god.
Yeah, pause 6. Obviously, I'm not
No,
gonna refer to
no, you
it.
said he was famous for being sad a lot and also talking a lot. I can't
Okay.
decide whether it is better or worse to meet him in person. What does he even mean?
Okay. I was being neutral.
No, for being sad a lot, dude, that is not a good impression of him. Okay, whatever. Um, sorry, we'll leave. Yeah, we're not doing the 2020 Incident Mode 2 problem. We're skipping that one. You guys can like, I think you guys should try it on your own. Like, don't look at the solution. Yeah,
Yeah,
like
yeah.
actually give it give it a good go if you haven't
Yeah,
done it
do the
already.
IMO problem. Yeah.
Yeah, this IMO problem is pretty good. It's pretty old. It's not super hard. Like, don't be scared by IMO.
Wait, but I mentioned them twice in the report.
Twice? What have you mentioned again for? Oh
Didn't
my God!
you?
Wait, is it because he didn't win his medal?
Yeah.
Wait, why did you put that one in? That was actually not funny. Crushed by the expectations that he has for himself of winning a bronze medal, which he will fail to fulfill over the course of the next 2 days. That is wild.
No, but he basically said himself on the Discord server, so I'm just
Yeah,
quoting.
but you can't say that. He can say it. You can't say it.
No, no. Okay, my
I'm
bad.
sending you a report. I'm sending you a report. I'm saying,
Wait, don't do it. Don't do it.
why did you write that in?
What if seeing you feel sad? No, but isn't it like kind of good that I wrote that because I was being a bit poetic.
That was not poetic, bro. What you like? Like the bro thought he was writing an actual novel.
Okay, fine. Maybe I was just a bit angry because he didn't
Nah,
recognize me at the opening ceremony.
but for now the exams and like, nah, bro thought he was actually writing a fucking book there.
Just like
Holy.
the team who didn't recognize me at the opening ceremony, at the closing ceremony.
Anyway, sorry. Does anyone have any ideas here on pigeons and pigeonholes? Yes, I love pigeons and pigeonholes. Yes. Wait, how do you do this question? Prove that from a set of 10 distinct two. Oh yeah. Okay, guys. So like, how many choices of like subsets do we have here?
Yeah, how many do we have here?
Like, if I gave you a set of 10 distinct numbers, right? How many ways can you choose to um like subsets? Let's not worry about destroying for now. Let's just think about how many ways are there of choosing two subsets. I think we did this question like in some like past like mine and Z like combi like tutorial. Not gonna lie. It's like if you have like a group of n people, how many ways are there of like choosing a committee or something?
Um, they probably haven't. Wait, no, they
Yeah,
probably haven't like
yeah.
attended the
Okay, cool.
lecture yet.
Marissa got it. That's nice. Yeah, it's just well, um, do
Well,
we count the empty set? I mean, I don't.
who cares about the empty set?
Yeah,
Let's
we can
just
count it. No, we can count it. Yeah,
let's
two
just
to ten.
count it.
Yeah, so you can like because every element you can either put it in the set or not put it in the set, right? Or in the subset. So it's like a binary choice for every element, do it 10 times, 2 to the power of 10, right? Cool. So we have 1,024 different subsets that we could possibly choose. But how many different like distinct so there these are our pigeons, right? 1,024 pigeons. And that's quite a lot of pigeons, right? So if the number of we want like the number of pigeonholes to be fewer than the number of pigeons. So the next question I guess is okay, I'm gonna quickly wrap it up because it's ending. How many possible sums could these subsets have? Like what is the like what is the range of values for 10 minus
That's basically true.
wait what is oh sorry what does that mean when you say like 10 minus 900 like
10 2,
990
10 2.
oh
10 to
10 to
9.
990 yes no yeah you're right it's the range is a little bit smaller right because you can't have like 99 like 10 times right it would be like 98 90 it doesn't really matter basically the important part is that the total number of possibilities is less than 1024 yeah actually I'm pretty sure no it's 0 to oh wait no distinct two-digit numbers. No, but okay, if we include an empty set, you can also have 0. Okay, it doesn't really matter, right? The important thing is that the total number of like possibilities is less than the total number of subsets, right? By pigeonhole principle, there must be two subsets that have the same sum. Cool. But we're not done with the problem because the problem says that we must have two disjoint subsets. So what it means for two subsets to be disjoint is that they share no elements in common. So if you have the set 1 and 2 and you have the set 1 and 3, those are not disjoint because they have the element 1 in common. So we need to remedy this issue. So like, what is like an appropriate, fix to this? It's not too hard. Like, suppose that we have two sets that have the same sum, but they are not disjoint. They share some common elements. How can we modify these subsets such that they are disjoint and still have the same sum? Yeah, good. So just take away the common elements, right? So now because you've taken away like equal numbers of the same numbers on both sides, the sums get reduced by the same amount, and they are both still valid subsets because they were originally valid subsets. You just got rid of some elements. They're still good subsets. They still have the same sum. They're disjoint now. Perfect. Life is good. We're done with the problem. Okay, cool. Everyone go now. Good job. Thank you guys.
We did it. Yep. Okay. Bye bye, guys. Good lesson today. Yep. Wait, Marissa solved the problem. She's the goat.
Wait, Egmo team next year.
Facts. Egmo team next year. We're making a 2 Egmo of this one. Wait, Chris. Who do you think is going to be deputy leader for Egmo? Like, Dawn says she doesn't want the position, right?
Bro, I'm gonna go convince her to like go take up the position.
No, I think it's gonna be Brina.
Yeah, fair enough.